So our next speaker is Barbara Gigerl. Barbara is currently a PhD student in the Secure Systems Group at Graz University of Technology. She's going to talk about Coco, which I guess is more like an approach or technique enabled by RISC-V rather than something kind of within RISC-V, right? Over to you.
Okay, can you see my slides?
Yes, you'll just need to, we see all of them. Never mind. That's good. I will tell you that there is a small black bar in the upper right-hand corner that is most likely the Zoom controls. Yeah. If you can move those out of the way, that would be fine. But if you don't have any content up there, then it'll be fine. I think it's okay like that, right? Okay. Yeah. Good. Okay, so welcome everyone. My name is Barbara, and today I will talk about Coco, which stands for Co-Design and Co-Verification of mask software on RISC-V CPUs. This work was joint work by my colleagues and me from Graz University of Technology. So in physical side channel attacks, the setting looks similar to this. So we have one attacker who has physical access to a cryptographic device. And for example, the attacker can use an oscilloscope to observe the power consumption of the device. In our case, this device is a CPU. And in that case, the power consumption will depend on two things. First of all, the instruction, which is currently being executed. And second, the data which is involved in the instruction. So the data which lies in the register file and the data memory. To prevent such attacks, we can apply the masking countermeasure, which basically splits any intermediate value S into multiple random shares. And the attacker can now or has to now observe all shares to be able to deduce some information about the native value. And as you can imagine, constructing such masked implementations is not an easy task. And therefore, we want to have verification tools which help us by doing so. And such tools can more concretely check the separation of our shares when a certain mask program or a certain piece of masked hardware is computing something. Okay, so those masked verification tools so far exist either for masked hardware circuits. For example, here you have Rebecca and mask-verif as one of the first tools. And basically, these tools check for a given mask circuit whether there exists a gates which combines two shares. And these checks are done in the so-called classical probing model, which defines the abilities as an attacker. In the classical probing model, the attacker has the probes, and these probes can be distributed onto the gates. And then the probes will deliver basically the value which are computed by these gates to the attacker. And most importantly, this includes glitches and transitions, which might be visible on a certain wire which is being probed. The second class of verification tools are constructed for verifying mask software in the so-called software probing model. And these checks are rather on algorithmic level and hardly consider the hardware or CPU, which is in the end used to execute the software. And the assumption is basically that the hardware is secure. So our processor does not introduce additional security threats to the software. Unfortunately, this is often not the case because as it is with every hardware, there can be glitches and transitions in the circuit. Therefore, what we want to have is a tool which can verify a certain piece of mask software when we execute it with a certain concrete CPU. And the CPU is best represented by a netlist. So after the synthesis and everything. And with Coco, we have such a tool. Now let's look at one specific example, which we have in almost every processor. We have a register file, and the register file can be a threat to your mask software. So this is a good example of hardware which might reduce the security level of your mask software. In this example, we have 4 registers here, and here we have a multiplexer tree which is used to address the registers. And here in the gray box, you see the software we want to execute. So we want to store x2 and then x1. Additionally, we know that we have a program which has 2 shares, S1 and S2, and the shares are in registers x1 and x2. Okay, so in the first cycle, we want to store x2, which means we have to read x2 from the register file. The multiplexers here get their respective value, and the value of S2 will kind of propagate through the circuit until we see the data at the read port. In the next cycle, we want to store x1, which means we have to read x1 from the register file. And what happens now is that this multiplexer here switches the select signal from 0 to 1, which leads to the output of the multiplexer switching from the previous value to the new. And we have a transition from one share to another, which means we have a leak in our program. This is, you might argue that this is a rather obvious case because you're kind of accessing your shares in 2 consecutive cycles, but there are cases in which it's not that obvious. For example, here we want to store x3 and then x4. When we read in the first cycle x3, this multiplexer again has the value 1, but this one kind of selects that the data from the lower part of the register file should be read in the end. And in the second cycle, we want to read x4. And again, this multiplexer switches from 1 to 0, which is why we have a transition now from the first share to the second on this wire. And this means we have a leak in our program, even though we do not touch any of the shares. And such situations are very hard to find without a proper verification tool. So this is why we constructed Coco, which basically takes a piece of mask software written in RISC-V assembly and the hardware which is used to execute the software. In our case, this was the RISC-V EBEX core. And Coco can then verify or prove that the software as executed with the EBEX core is secure or does not introduce any leaks in the context of masking. We cannot adapt the classical probing model, which we already saw for hardware here, but we have to kind of make some constraints to this classical probing model. Because in the classical probing model, the attacker can kind of observe a wire for an infinite amount of time. And if we do that in a CPU, the attacker can simply choose the register file output and observe it for an infinite amount of time. So for all the cycles, the program will last. And then our scheme is immediately broken. So we constrain the classical probing model by the notion of time. What does this mean now? The attacker has again D probes and can use one probe to measure information at one specific location, but also in one specific clock cycle. So this means the probes can be distributed to be either at the same location in different clock cycles or at different locations in the same clock cycle or a mix of both. Let's have a look at the co-verification flow of Coco. So here we have again our software and the hardware, and the first step is to simulate the software execution with the hardware. There we get out a dump of control signals, which kind of maps the software to the hardware in terms of control signals. Next, we perform an annotation, which means that we tell the verifier where the shares and randomness is located. So in which registers is the first share, for example. And this is done on bit level. of course, we cannot only annotate registers, but also memory locations. And these two things are then given to the verifier. The verifier will run the verification for a few cycles and then output, yes, the execution is secure, or no, it's not secure, and there's a leak in cycle 8 at a specific gate. Okay, so the co-verification methodology itself was inspired by Rebecca, which is a pure hardware verification tool. And we extended it such that we can execute mask software on a concrete CPU netlist, so on a hardware. And it works roughly like that. We have the labels, which we saw earlier in the annotation step, and we propagate these labels through the whole CPU netlist. And for each gate in the CPU netlist, we then compute the so-called correlation. The correlation will tell us if there is a correlation to a native value, which we don't want to have, and can either be stable or transient. Transient means that glitches and transitions will be taken into account. Let's have a look at a short example. So here you see a circuit, which consists of wire A, which comes out of combinatorial logic, and a wire B, which comes out directly of a register. And both inputs then go into an AND gate. And in this case, the value B would be our control signal. And here you can see the dump of control signals for 3 cycles, n, n+1, and n+2. And you see that B first is 1 and then switches to 0. So the output of X will basically first be A and then 0. When we now want to compute the correlation of X, we would first of all focus on the stable correlation set. So in the first cycle, since X displays the value of A, X will correlate to A. But then, since X switches to 0, it then correlates to 0 or a constant. The verification tool does not make any difference between constants or the 0 set you see here. Then, for the case of the transient correlation, we also have the same in the first cycle, but in the second cycle, we have to add A to the correlation set. Why is that the case? Because B switches from 1 to 0. So for a short amount of time in the first time frame of the cycle n+1, we will still see the old value of the wire A until the 0 from register B will propagate to the AND gate. And in the next cycle, we can safely assume that X does not correlate to A anymore because B has been stable 0 for 2 cycles now. And this is a quite nice concept which we also applied to the register file. So to construct a secure register file, which you see here. So we placed a gate before each register, and this gate determines if we will see the register value at the gate output. And as a gate value, we use the one-hot encoded register address. So in this register here, at most 1 bit will be 1. And this refers to kind of the gate is open and we want to read the register. If we now consider the example where we want to store X2 and then X3, we see that in the first cycle, X2, the gate of X2 will be open, and therefore the data can kind of be seen at the read port. And in the next cycle, we will have the data of X3 here at the read port. So at most, we can see at the read port the value of 2 registers. And now let's come to the second part of Coco, which is called the co-design. We conducted a case study with the RISC-V EBEX core. And the EBEX core is a rather small core, a 32-bit core, with which is in order and has a two-stage pipeline. And yeah, is applied rather to small IoT devices and smaller use cases. And then we tried to harden the EBEX core with Coco against side channel attacks. So what we did was we constructed a set of mask software implementations and then tried to verify that software implementations with Coco. And yeah, Coco reported a whole list of leaks. And these leaks were in various parts of the CPU, and we had two strategies to remove these leaks. First of all, sometimes we decided to do changes in the CPU or in the hardware itself. So this would, for example, be the same as we did in the register file. We introduced this gating mechanism to enable secure register reads. But sometimes changes in the hardware are too costly and we rather want to adapt the software. And this is what we call the software constraints. The software constraints are basically a set of rules. And if these rules are followed by the programmer of the mask software, this already helps to prevent some known leakages. And of course, if the software does not meet these software constraints, Coco will report it by pointing out that there is a leak in a certain cycle at a certain gate. Okay, let's have a look at an example of how a software constraint could look like. So here we have our hardened register file again with two shares in the registers. And now we want to first store x2, which means we see the value of the second share at the read port A. And then we want to store x1, which means we create a transition here. And the software constraint to prevent such kinds of leakages would be that shares of the same secret must not be accessed within two successive instructions. So between the two store instructions, there should be another unrelated instruction, for example, a NOP, which prevents this transition at the read port A of the register file. Okay, then we also found some further problems in the core. First of all, we found out that there is a hidden state in the load store unit, which is basically a register. And every time you store something to memory, this register gets the value of whatever you want to store. So this could be bad if you store two shares, because then you have a register override. Another thing were the computation units, so the ALU, the multiplier, and the CSR unit, because they were always computing. So if we kind of, for example, execute a load instruction, still the ALU would compute the XOR without being needed. And this specifically creates leaks when you want to use parallel masking schemes. So in these parallel masking schemes, you do not place all the bits of one share in one register, but distribute all the n bits of one share to n different registers. And then this means that one register will then store the different shares of the same secret. And in the case of, for example, the CSR unit or also the multiplier, some parts of that combine the bits of one register. And this creates a leaks because your bits are two shares. And one point is also the communication with the data memory. So there are strategies you can follow to have secure loads and stores from and to memory. But I won't go into detail about that right now. If you're interested, you can simply have a look at our paper. Okay, now let's have a short look at our evaluation. So the total overhead of the security measurements we built into EBEX is about 10%. So we compared here the basic design without any security feature to the design which has all security features enabled. And we also tried to do some small benchmarks, so to benchmark our tool. For example, here we tried some simple AND gates, but also some broken implementations. Broken means that the software constraints, which I showed you before, were not met by the software. And yeah, Coco in this case pointed out that the 12th cycle is the problem. We also had some bigger test cases like the AES S-box and also some higher order tests like a Ketchuk S-box and a third order DOM AND gate. Yeah, so now I want to give you a short outlook on what could also be done with Coco. We managed to analyze a bigger core also, the RISC-V Swerve core. The Swerve core is also a 32-bit core, is also in order, but has a dual issue pipeline, which means it can execute 2 instructions in 1 cycle. It also has, instead of 2 pipeline stages, it has 9 pipeline stages, so it's bigger than the EBEX core, and also has some other applications like automotive or more data-intensive IoT devices. And in our analysis, we tried to find out whether these pipeline stages or execution units or data caches in the core have some effect on the security of masked hardware, of masked software, sorry. Yeah, and we could do that with the Coco tour, and just to a short outlook, we managed to show some interesting properties of those pipelines in the connection of masked software. Yeah, so in summary, there exists what we call the hardware-software gap, because formal proofs for masked software often do not consider the hardware as it should be. Therefore, we can have Coco, which helps with the co-verification of masked software on concrete CPU netlists, and also with the co-design, such that we can find some patches for the hardware and also constraints for the software for a specific CPU. Here in this talk, I presented the case study about the EBEX core, which you can, if you are interested, also read up about in our paper. And if you're interested about the second case study with the Swerve core, you can also find it here in the paper. And yeah, I also included the links here. So this was basically my presentation. Thank you very much for listening. If you have any questions, I'd be happy to answer them.
Yeah, thanks very much, Barbara. That's really interesting. We have got a couple of minutes for questions if there are any. Okay, so a long one in the chat window from C. Let me read it out for you. So, do the proposed revisions security patches, e.g. gated or unused computational units, have an impact on the verification performance?
On the verification performance, yes, it kind of did, because for the case of the computation units, which were kind of always computing, we also introduced such a gating mechanisms such that the ALU, for example, would be turned off when we do not need it. And therefore, of course, the data will not enter the ALU anymore during verification. And this, this kind of cuts away the ALU from the verification process, and this increases the performance. Yeah. And yeah, about the second part of the question, yes, we could actually apply Coco also to ARM processors, but the problem there is that we do not have the netlist. So the netlist of the processor is not public, and yeah, without a netlist, we cannot do the verification. And yeah, but if the netlist were public available, We could, of course, just apply the same approach we have with Coco for an ARM assembly executable and for any ARM core you wish. I hope this answers your question.
Great. Okay. So we're kind of up against time. So if there aren't any other questions, then I think we thank Barbara and move on to the next talk. Thanks a lot.